Good morning. So today's lecture, we are going to continue our study of graphs. So we're going to do it's basically a 4-lecture series on graphs, of which this is lecture 2. And in today's lecture, we are going to break down graphs even further with this idea of performing what is known as depth-first search. So depth-first search will allow us, as one algorithm that we can use to find a path, and if one exists, between a specific node and another specific node in the graph. And then if we want to find all of the potential paths from the origin to all of the nodes, we perform what is known as a topological sort. We're going to study today as well. And then if we want to find the shortest path in the event that the graph is that the edges are weighted, then we are going to perform what is known as Dijkstra's algorithm. And I'll show you how to implement that in code, and we will see the solutions to these particular program challenges. So in today's lecture, we're actually going to see several other data structures and how we're going to implement them to solve these challenges. So depth-first search. The idea behind depth-first search is that I start a specific node, and then I'm going to go to the first vertex that I have with an edge. So in an adjacency list representation, the edges are ordered. So I would want to go to a specific edge first, and then I move to that node. And then once I move to that node, I then evaluate all the edges, and I would go to the first one, and so on. I can't go much further, otherwise I evaluate social distance. You get the general idea. So what will happen is we keep going until we each reach the end of a potential path. Once we reach the end of that path, then we start moving back. And so when we move back, we have to keep track of which ones we actually did. So we have to evaluate specific data structures that we need to do so. And so, hold on, sorry. And so this is a crucial aspect here. Since we are treating this as a set of subproblems, it's kind of a form of dynamic programming, where we know places we've evaluated and places we still need to go. And based on that set of solutions, we can come up with a total final solution. And since we can do that, and since we're searching, we want our solution to be recursive. And one of the reasons why this is essential is because when it's depth-first search, we only know where we're at. Just like I was talking about in the last lecture, how we're trying to find directions from the ballroom to one of the hotel rooms. If I only have the information in the node, I only know where the 3 doors are and that there's an edge going out. And then when I get to the next node, I can make a new set of decisions. And so that's what depth-first search is. And when we do things recursively, we are putting everything onto the instruction stack. So each set of each recursive call, we can keep track of which edge we've evaluated, and then we just iterate through all the edges. And we only iterate through in the event that we have not actually found the destination. So by using the instruction stack, which is actually a form of using a stack type of thinking. So we're actually going to implement a stack data structure in our solution. And so keeping track of visited nodes, one thing we have to do is we have to make sure that we know if we visited an edge or not. And so in order to do that, we want to use some sort of data structure to ensure that we can look it up. And in this case, we just want to look it up, make a decision, and continue on with the algorithm. So we don't want to use a linked list, because in a linked list, we'd have to go through every single node until we found the specific location. So that's a big old runtime. Likewise, with a dynamic array, we don't want to use that, because even though we have direct access, we still have to go through and look for each individual element, which is still big old time. So we want to build off of the dynamic array and use hashing. So in order to solve this, we're going to use a stack and we're going to use a hash map. And remember that a graph itself is built on a dynamic array where we have a set of edges. So we have several data structures that we're implementing in order to be able to implement the graph and solve the algorithm. Let me check the question in the chat. You can't hear me. Do you hear me now? Look, it's giving me sound that you hear me. Okay, yes, good. Okay, so we see that we're using several different data structures, plus we're using class aggregation, because first we built an edge, then we built a vertex, then we're using those to represent elements in the graph. So everything we've learned up to this point, we are combining together in order to be able to implement these algorithms. So what I want to do first before we dig into code is go through an extensive animation of how depth-first search actually works. On Friday's lecture, we're going to learn about breadth-first search. We briefly learned about it when we were implementing the matrix, and we learned that we're going to use a queue. So we're actually going to implement a queue in our solution. That's going to happen on Friday. But for now, we're going to use stacks. And the way this is going to work is we have our adjacency list representation that correlates to the specific graph. And then we have two things that we're keeping track of here. We have visited verts, and that's going to be a Boolean to indicate whether or not we have actually visited. And if we visited it, we don't want to evaluate it again. If I've gone through here, there should only be one valid depth-first search path from any given node. The second one is visited edges. And in visited edges, that's going to keep track of which edge I have most recently evaluated. So therefore, when I go back up to that specific recursive level, I will move on to the next edge and evaluate the destination vertex. The next part is this data structure of parents. So I've created a list, actually not a list, I've created an array of all the locations. And what I'm going to do is I'm going to fill out its parent. So for example, let's say the depth first search is 4, 20, 30, and 18. That means 18's parent is going to be 30, 30's parent is going to be 20, and 20's parent is going to be 4. And we're going to set 4's parent to be -1. So once I traverse back up, if I found it, and I will stop that portion of the algorithm, when I find a node with -1, that means that is our origin. And then I'm going to keep track using a stack and the final solution. So let's start and discuss what's actually going on. So I'm going to start at 4, if the mouse ever allows me to. There we go. Okay, so we start at 4. I've identified that as the origin. I have set its parent is -1, and I have set visited verts to true. Does everybody see that so far? Furthermore, that's where we're going to be on the stack. So now we have these two edges. So which edge are we going to evaluate first? Does anybody know? If we're using depth first search and we're evaluating it in adjacency list order, which edge and vertex do I want to go to next? Notice how I visited edges of 0. So if I have an array of destination vertices and I'm currently at the 0th element of that array, which one do I want to go to? Yes. The first one, right? 20. So now what's going to happen is you're going to see that 20 is going to show up. We're going to go to 20 next. We're going to put 20 on the stack. We're going to set visited edges, we're going to set visited verts to 1. And we're going to say that 20's parent is 4. Does everybody see that? So let's continue. So now I'm going to move to 20. So now at 20, which vertex should I evaluate first? Yes, we want to look at 4. All right, so I was just checking the chat to see if anybody had answered. So we want to look at 4. So here's how the depth first search algorithm is going to work. It's going to say, well, 4 has been visited, so we're not going to go to that. So then, what's the next vertex we're going to visit? If I've visited 4, yes, in the back. 10, very good. So now we're going to look at 10. The way we do that is we are now going to update visited edges here. We're going to see that visited edges on 20 is going to update to 1. We don't want to do 4. So now we're going to look at 10, and we see that visited edges is 2. So now we've checked both of these. Does that make sense to everybody? So now what's going to happen is I am going to put 10 on the stack. I am going to mark 10 as visited, and then I'm going to mark 10's parent as 20. So when we move over here, that's what goes on in this portion of the animation. Okay, so now I think we might have a little bit of a hang of it. So which vertex do I want to evaluate first? Based on the adjacency list representation. Yes. We would do 5. Okay, so forgive me, I understand exactly why you're doing that, but I want to kind of go over why it is that you came up with that answer. So first, we're going to evaluate 20, but 20 is visited. So therefore, we don't go any further. So then the next element in the adjacency list is going to be 5. So that's exactly right. So now what's going to happen? Let's see the pattern here. What's going to happen in all of these little data structures when we move to 5? And the 3 crucial things we're going to evaluate are these 3. These 4. So what's going to happen first to the stack? What are we going to see when I click the next animation? What will be there? Yes, very good. We're going to put 5 there, so we're going to see 5. So now what's going to happen to parents? What's going to change? Yes. Very good. 5's parent will become 10. What's going to happen to visited edges? Well, we've already updated to 2, so we're just going to move there, and that's going to be fine because we haven't evaluated anything from 10 yet, right? So we want to leave it as 0. And last thing, what's going to happen at visited verts? Believe in yourself. I believe in you. See if anybody said anything in the chat. What's going to happen with visited verts? What's going to be changed? Sorry, you screwed your hair, but now I'm going to pick on you. What's going to happen there with 5? There's an arrow pointing to it. It's going to go back to the parent. We haven't gone down to 5 yet. So when I go from 10 to 5, what's going to be updated in that visited verts data structure? It will be, oh, I see. The second element is going to be, yes, very good. So that's going to be a Boolean. So now we're going to set it to 1. And that is exactly what's going to happen. So now we have 5 on the stack. We now have set 5's parent as 10. And then we have now set 5 as visited. All right, let's keep working through it. So now we're at 5. Yes. Absolutely. Visited verts is a Boolean indicating whether or not we've evaluated that vertex or not. All right, so now we're at 5. So which vertex are we going to evaluate first? Yes. We're going to evaluate 4. Have we visited 4? Yeah, probably, now that you're thinking about it, once it starts feeling simpler, then the answer is going to start coming fast. So have we visited 4? Very good, a lot of head nodding, so yes. So we don't need to go to it. So now what are we going to evaluate? Which one are we going to evaluate next? Yes, 10, very good. So now we're going to evaluate 10. Have we visited 10? Yes, we have. So this is the next step. We've evaluated all of the edges in 5, right? So now we know that there does not exist a path from 5 to 18. So now what we're going to do is we have reached the end of that recursive call, which means we're going to take 5 off the stack, and then we're going to continue evaluating in 10. So you're going to see 5 come off the stack. So we can't go to 4, can't go to 10. So now you're going to see this big red arrow has gone back to 10. And the reason why it goes back to 10 is we had 5 here. We popped it off of the stack because now we're done with that recursive call, which means now we're evaluating what's at the top of the stack. And the crucial part here is we have visited 2 edges, right? So now we want to evaluate 0, 1, and 2. So now we're going to look at 18. Does that make sense to everybody? So that's how we use the stack, and specifically the instruction stack, to keep track of everything. So now what we're going to see, so now let's walk through it. All right, we're going to move from 10 to 18. So what's going to show up on the stack? Have confidence, I believe in you. 18, very good. What's going to show up in parents? I'm sorry, what was that? 10 is the parent of 18, very good. What's going to show up in visited edges? We're going to change because now we've evaluated this. We're now going to have 10 is 3. And now what's going to happen to visited verts when we move there? Which one are we visiting? 18, right? So what's going to happen in visited verts? It's a Boolean. Very good. We're going to change 18 to 1, right? So that's what's going to happen when I run this animation. And now we've updated everything. And so guess what? We've now found it, right? So now that we've found it, we're going to, okay, so that's topological sort. I'll leave that be. All right, so now that we've found it, we're going to remove everything from the stack. Now we're all the way back, and then this is where this data structure becomes useful to determine the final solution. So now I want to say, what's the path? I have 18, right? So the final solution is going to have 18, and then we look at its parent, and its parent's going to be 10. Then we go to 10, and we see that 10's parent is 20. Then we look at 20, and we see that 20's parent is 4. And we go to 4, and we see that 4 is -1. So therefore, the depth first search pass is 4, 20, 10, and 18. Like so. And that is our final solution. Yes. That's any path. So basically, the depth first search is dependent upon the ordering that we put into the adjacency list. So shortest path is something we're going to go over later, and that's going to be dependent upon weights in the graph. All right, let me check. Okay, so it looks like we have 2 comments in the chat. First one is 5 will become 1. Very good, Brandon. And then what happens to 5, which is popped off? So in this case, what happens is when we pop everything off and we're evaluating everything, when we're done, we are going to just go back and evaluate it. Now this graph that I showed here is something I'm going to show you a little later on called a topological sort. But first what I want to do is I want to show you the actual code. So in graph.4, I have the first implementation of depth first search. Yes. Yes, and I'm going to show you an example of this in a moment. Okay, so first I have a public depth first search method that is called. And what we're doing here is we're going to set everything up before we make the recursive call. And then also in this depth first search method, I'm going to print out the results. And so what I want to do with you is I'm going to walk through step by step what each of these lines of code are, and to show you how we make these kind of decisions. So what happens is, let's find the destination. In this iteration of the code, we assume it starts at the origin, at vertex 0. We're going to learn how to do this a little later in this lecture, what happens when I have an origin and destination. So here I say if the input is invalid or the graph is empty, so there's two things. I have if destin is greater than or equal to vertex length, let's say I ask for, I have 8 vertices in the graph, the adjacency list is going to contain 0 through 7. So if I enter 8 or greater, that means I cannot possibly find it. Furthermore, if I say the length of the vertices is 0, that means I don't have anything in the graph to search. So therefore, I shouldn't be trying to search through an adjacency list that is empty. So therefore, I tell the user that's invalid. I'm just going to return. Let me zoom in a little further here. All right, so now I want to track the parents. So I'm using a dynamic array. We're using the dynamic array that we wrote in lecture. So I'm creating this dynamic array of parents, and I'm setting it to the length. And then I have that Boolean visited, which I called in the animation visited verts, and I also set that to the length. Then I create a stack, which we based off of a singly linked list, which I call final path, and that's going to be that last sentinel that we used. And then I have bool found equals false. So now I want to initialize all of these data structures so we can run the depth first search. I initialize the search. I say parents of 0 is equal to -1. So that if we do find it, I can use this as a way to terminate going back up like I showed in the animation. Then here, what I'm doing is I'm iterating through all of the vertices and I'm setting visited equal to false. In this line of code, I've accounted for the situation in which the user is trying to find a path from the origin to the origin. I say, well, if the destin is equal to 0, that means we've found it. I'm just going to set it equal to true, and we're not going to worry about anything else. So otherwise, we are now going to have our private recursive call. In that recursive call, I'm going to pass the destination, I'm going to pass the origin, I'm going to pass the parents, I'm going to pass visited. So does anybody have any questions about this before I go to the private call? Yes. That's okay. Ask it. Okay, so the reason why you, in this particular case, we're using a dynamic array, is because the lookup is just, it correlates to the specific location. Right? So that reduces two things. One, it reduces the need for us to develop a hash function. So we reduce the amount of code that we need to write. And the second part is that if I have an array with the exact number of elements, and I know exactly how to get there, and I can do that in big O of 1, by not using that particular hash function, we don't need to have that potential twice as much in order to perform the operation. So I've cut the memory in half, I've cut the work in half, or not in half, but I've reduced the need to write a hash function to be able to do that. We could use standard unordered map, and basically instead of using this, what we would do is we would say the key is the location and the value is the location, but it's redundant. So when I made this design choice, I used a dynamic array instead of a hash table. But it is a good type of thinking because you're ultimately what you're thinking is big O of 1. I want it to be fast. Well, it turns out I can accomplish the big O of 1 and reduce the amount of time. So that's why I made that. Let me check the chat to see if there's any other questions. We have 2 comments in the chat. Kyle, can you please repeat what that 0 in the input is for? And here, are you talking, Tiani, are you talking about 0 here in 211? Okay, so if you are talking about that, this is to indicate in the DFS function. Are you, I'm still a little confused as to what you mean. You can, I'll go through. So 0 here indicates the origin. So in this particular version, I'm going to show you a different version later, we're going to assume that all the searches start at the origin for simplicity. Did that address what you're asking about? The third put into DTS. Okay, I haven't explained that yet, so I'm going to explain the private call in a moment. Okay. So well, I'll come back to you after I go through everything, and this will hopefully make it clear. So let me go up to the private. Okay, no, not a problem. Okay, so here we have the private call. Actually, and I'll just do that for simplicity. Okay, so in the private call, this is where we're going to do everything where I want to make a copy of the stack. So I have one public call where I'm initializing everything, and then I have this private call where it's going to represent the stack that calls to the instruction stack. So here I have the int destin, the unsigned int vert val, and then I have the dynamic array for the parents and the dynamic array for the visited. So what I had in this is I had the destination, and then I start out with 0 in the public call, because in this case, I want to start at the origin. Here's another really good example of why call by reference is beneficial. So now we have a dynamic array. We have multiple dynamic arrays, of which we could have any number of nodes in a graph. And if we pass or call by reference, we're only passing a 64-bit pointer on every stack call instead of making a duplicate of the entire graph. So this is significantly reducing the amount of memory we need to solve the problem. So here we had the destination and we had 0. And so in the first call, we check to see if it's been visited. You may have noticed in DFS that I didn't mark it as visited yet. So this allows me to be able to keep the consistency of the recursive calls the same. And that's why here, at this line of code, I have marked visited vert val to be true. And so otherwise, if it hasn't been visited, we would move past this if statement. All right, so before I continue, Tiani, did that address your question as to why I called 0 initially in that function call in the public? All right, glad to hear it. Okay, so let's continue. I'll just press enter again so you can see. All right, so for this for loop, what's going on in the for loop is I start at 0 and I'm iterating through each vertex. Here's that function I wrote where I presented in the previous lecture about the number of edges. So inside, I go through each edge. And then I create a temporary edge, and this is kind of to make it simple for coding. And I say, well, I take temp edge, and remember, the edge has a destination value. So I know where I'm at the origin, I can check the destination. And here I'm checking to see if that destination has been marked as visited. In the event that it hasn't been visited, what I do is I set that array of parents with that edge destined equal to vert val. And what's going on in this line of code that I have highlighted is what would happen if I know the destination, I set its parent equal to the origin. So vert val, the first call is 0, but as we progress further, we're going to see that I can use parents to keep track of all the previous elements. I have one other element. Before I make any more recursive calls, I check to see, now that we have everything set up to evaluate the solution, if temp edge destin is equal to the destination, then we found it. No more recursive calls needed. And you see here that I have if check is equal to true. I mean, if check, return true. And this allows me to iterate through and find everything. So now what's going to happen is, if I didn't find it, then I'm going to make another recursive call, where I'm replacing what was initially 0 with temp edge destination. So now let's say that I'm looking from 0 to 7, and 7 is still going to be passed here, but now let's say I had 0, 1, and 2. Temp edge destin, initially, the first time through will be 1, and the second time through it'll be 2. And then I call parents and visited by reference again. And so now we're building those stacks using recursive calls. This last part, if that recursive call returns true, right, is true, then what I'm going to do is I'm going to say, all right, I need to return true every single time. Otherwise, what will happen is if I don't have this here, it will go back and try to evaluate the next edge. So this particular if-else statement, this particular if statement is ensuring that if we made a recursive call and it was true, we're gonna take that call off of the stack. So now this is another efficiency in the code. And so if I can't get through any of these two, then the last thing, we made it all the way through this particular call and it was false. Right, so does anybody have any questions before I show the rest of the public depth first search? Okay, so now I'm going to scroll back down here, and where we were in the private is we did all of that work, and now we're only doing it in one line of code. Line 213, I make the initial recursive call, and the last thing that's going to come out is whether or not it's found. So what we say, if it's not found, no valid path from 0 to the destination. Otherwise, now we are going to print out the results. And this is where we do that last step. So here I call it sentinel on an unsigned integer, and I set it equal to the destination. And then what I'm doing is I'm using a stack, and I'm putting that destination as the first element in. And now in this while loop, what I'm doing is I'm saying while the parent sentinel is not equal to 1, push that value onto the stack, push that parent on there, and then send the sentinel equal to its parent. So that's what we did in that last part of that animation. We went from 18 to 10, and so now what I'm doing is I'm pushing 10 onto the stack, and then I'm updating sentinel to 10. So then when I move to 10, yeah, this is 20. So 10's parent is 20. So now I'm pushing 20 onto the stack, and I'm updating sentinel to 20, and then I do 20 to 4. I push 4 onto the stack, and I update the parent to 4, and that's when I get to that last time where I check 4's parent. 4's parent is -1 because we initialized it in the algorithm, and therefore, once we go through that and pop everything off the stack, it's actually going to print the exact path. And that's what we do in this final while loop. I say the valid DFS path from 0 to the destination is, and then we use the last in, first out, 4, 20, 10, 18 is what's going to print. Does that make sense to everybody? All right, before I continue, does anybody have any questions? All right, so I showed you all that, showed you all that, showed you all that, showed you all that, showed you all that. All right, so depth first search .cpp. So now I'm actually putting in the exact graph that was shown in the animation. And then I put in all the edges. And so I use the location. So 0 and 1 is going between 4 and 20. Does everybody see that? And then what I do is I print the graph. So I have an overloaded operator that prints through everything. And then I conduct depth first search on 5, 4, 3, 2, 1, 0, 6, and -1. Now notice that we have 6 elements. So when I call 6, it should say not valid. -1 should also return not valid. So now what I want to do is make DFS, and let's see what the actual results are. The graph that's printed out is exactly what we anticipate. It's unidirectional. So for example, we have 4 goes to vertex 1, starting at 0. So that's 20. And likewise, we produce the exact graph. And now we see this path. So 0, 1, 3, and 5 are the vertex indexes. And so that becomes values of 4, 20, 3 is 10, and 5 is 18. So now we've correlated the algorithm to our values. So from 0 to 4, it's 0, 1, and 4. So 0 and 1, 1 is 20. And we see that there's an edge from 1 to 4. And so we get our depth first search that way. And we test everything, including finding itself. And so that's what happened there. And then the last part, invalid inputs twice, just as we predicted with our secure coding at the beginning. All right, does anybody have any questions? All right, so now, probably the logical follow-up question you might have is, well, that's all well and good, but what if I want to find a path from between 2 nodes that are not in the origin? That's not the origin. Can I find it? So it turns out we can write a different version of this algorithm with very minor tweaks because of the way we have it set up. Remember, in the first one, we were dependent upon knowing that we started at the origin. So what we can do with this depth first search is we just take in an origin and a destination value, and then we test to make sure that both inputs are correct from the user. And then instead of saying, well, the visited 0 is equal to -1, we just set that index equal to -1, and then we pass the origin instead of 0. So Tiani, that's kind of the follow-up on the question that you had. We want to make sure that we are passing that origin, and then the rest of the algorithm is going to work again. So all we need to do is write a public version to set everything up, and then we can use that same private call as we did before. And so the only change here in depth first search is in graph5.h, we bring in an origin and destination, and then I check origin as well as destination for validity. Before, we had parents of 0 is equal to -1. Now I'm setting parents of origin equal to -1. Before I had if destin is equal to 0, now it's if destin is equal to origin. And then instead of passing 0 in the algorithm, I'm passing the origin that the user requested. Otherwise, it's completely the same. And then when I'm printing out the results, instead of saying no valid path from 0 to a variable, I change that to origin. And then likewise, when I'm printing out the valid results, I say no, the valid path from origin to destination is, and then print those out. Otherwise, we're just using the same destination, and because we're using the sentinel in this way, the moment we hit the origin that was put in, its parent is going to be -1, and therefore that port is going to work the exact same way. So we don't need to make any changes. And so in make DFS2, I've done the same graph, but now I have several paths that I've put in, including a couple that aren't going to be valid because I have 6, which is not a valid node, and I have a -1 in there as well. So I'm testing all of those cases. So make DFS2. We have the paths. Notice how I have 3 to 5 and 1 to 4, but I'm also testing 2 to 4. There's no valid path. And then I go from 4 to 1. So I'm trying to go backwards in a unidirectional graph. And so that correctly indicated that there's no valid path. Likewise, I put in the origin and destination as both 1, and so our algorithm caught that as well. And so does anybody have any questions before I continue? Okay, so based on this, we can perform what is known as a topological sort. In a topological sort, we start at the origin and perform breadth first search, and instead of stopping when we found something, we just go all the way through, and this gives us, if we were doing breadth first search from the origin, this gives us the path to every node in the graph. And for now, we are assuming that we have a connected graph where this is possible. And what's going to happen when we return this, that stack that contained all the results is going to contain the topological sort. And the difference is we're actually going to return a different graph that is going to contain all of the edges that we need in our topologically sorted graph. So for example, remember that the depth first search from 4 to 5 goes like this. And the reason why we have to do depth first search in that way is because we investigated 20, which investigated 10, which investigated 5, even though in the original graph, there was an edge between 4 and 5. So that animation that I showed you actually went through the entire topological sort. Hey, does anybody have any questions on that? So just a quick history. Where topological sort came from was it was the computing company, it was actually called the computing company, was approached, and they were trying to come up with a dependency chart to help evaluate their employees' performance. And so this is the actual graph that was shown that allowed us to be able, that they used to test their program evaluation review technique. And so the difference between topological sort, as I indicated, you don't check for a found vertex, you evaluate every possible vertex. So in graph 6, what I have done that's different is I have a public topological sort method. Here it is. And so I create a graph, top sort graph. And then what I do is I add each vertex, I just get the vertex value. I haven't put in any edges yet. And I add those to the new graph. And then I set up using the parents and visited vertices just like I did before. I create a final path just like I did before. And then I iterate through and I set each of the visited elements to false, and I set the parent of each of them to -1. And what we're going to discuss next week is if this comes up and there's no way to reach a node, then the graph is disjoint, and this is known as a disjoint set. So now what we're doing here is I iterate through, and we're running depth first search from every single, to every single node from the origin. So I have a private call, and the only difference between the topological sort's private call and the depth first search is we just keep going until we're out of edges. We do not have a case in which we would stop. So let me show you that up here. It's the exact same thing. We're checking if it's not visited. We set that to true. And then we get the edge. We iterate through each edge. And then we set the parents, just like we did before, except you'll notice how I don't have a Boolean, and I don't have that case that says we should stop if we found something. So I'm running, so hold on, let me scroll back down to the other topological sort. DFS, top sort. So we run that to every single possible destination from the origin, and then I track the parents for printing the results. And then what I'm going to do is, I'm sorry, here we go. We have the loop for a top sort. And then what I'm going to do is I'm going to get the destination and the origin and use those in that as an edge. And I'm going to add the edges to the new graph. So we see that I have parents iter, and edge weight. So I'm adding these edges to the graph, like so. And here I'm getting edge value, and if you remember edge weight, that's called by reference, so I can return that. And then I add that, and so what's going to happen is the graph that's returned here in top sort graph is a subset of the final graph. And that's what we want. So when I run topsort.cpp, I have the exact graph from the slides. And then what I'm going to do is I'm going to print the original graph, and I'm going to run depth first search on these sets of nodes. And then I'm going to run the topological sort algorithm, and then I'm going to run depth first search on the same nodes. And if the topological sort algorithm worked, the solutions should be identical. Oh, and we see here that we have the full graph, like so. We have a reduced topological sort graph, but we see that our solutions for the original graph step first search and for the topologically sorted graph are the same. And if you get that, that means your topological sort has worked. Okay, so does anybody have any questions? Okay, show me that, show me that. And there's the result comparing the topologically sorted graph. Okay, so it is 11:13. What I'm going to do is there is a question about shortest path on the homework assignment. So when I get back to my office, I'm going to remove that from the assignment, and I'm going to start Friday's lecture here, which means I'm probably going to modify a little bit of next week's disjoint set lecture as well. All right, so does anybody have any questions before I dismiss? Let me check the chat as well. We do not have anything in the chat. Yes. Okay, so when a topologically sorted graph is when I have an adjacency list representation, the final graph would be the result of a depth first search to every node in the graph. We call this topologically sorted. It's kind of like topological to geography. So in this case, the question is, if you understand why this edge is not in the topologically sorted graph, you'll understand the whole thing. So let's break it down. So we start at 0, and 4 has outgoing edges from 1 to 2. When it's topologically sorted, we mean that we check the edges in the order that they are in the adjacency list. So therefore, we would go to 21st, and then we evaluate 3 and 4. So 3 is here. So we have to go to that one first. And then we see 3 has 5 and 2. Well, we'd go here and there's nothing, but then 2 is there. And so because of the way that it's sorted in the adjacency list, we say that the correct topological sort between these two vertices is 4, 20, 10, and then 5, not 4 to 5. Does that make sense? So that's what we mean by topological sort. Any other questions? All right, so it is 11:15. On that note, you were all dismissed. I'll see you on Friday.